Dear fellow scholars, thank you for being here to watch this presentation. I'm Jiang Tao from Tsinghua University. Here, I'm going to present a dynamic mixture model that is suitable for simulating non-equilibrium multiphase fluids. The background picture demonstrates a mixture of two fluids. One is pink and the other is blue. The pink fluid is under control and forms a teapot shape. I shall explain later about this non-equilibrium property. Let's begin the presentation. This presentation starts from a simple introduction of the mixture model, which is used to simulate multiphase fluids. We will see that the previous mixture model has its limitation in simulating highly dynamic scenarios. That is why we need a dynamic mixture model. I will briefly introduce this new model and the corresponding simulation workflow. That is followed by the video of our experiment results, and finally comes the conclusion and discussion. Here, let's first watch a video showing some bubbly wine being poured into a glass. The liquid and the gas are quickly separating, forming a floating bubble layer. This quick separation process is achieved by our dynamic mixture model. When we simulate multiphase fluids, we need to handle the interaction between the fluids. For example, we may simulate the mixture of alcohol and water. Some methods use one set of particles for each phase, but the mixture model uses only one set of particles to represent the whole mixture. As shown in this figure, we can only see one set of particles, each of which has different color, as they have different amount of the component phases. The particles' velocities describe the overall motion of the mixture, but what about the relative motion of the individual phases? Well, these motions are represented by the phase transport inside the fluid body. That is, the motion is decomposed into the overall motion and the relative motion. Since there is only one set of particles, each particle carries more information than those in single-phase solvers. The most important multiphase information is the volume fraction of the component phases. Then each phase has its own velocity. By averaging these velocities, we get the mixture velocity. This is actually the particle velocity. The relative velocity, also called drift velocity, equals the phase velocity minus the mixture velocity. So we have the mixture velocity that describes the overall motion, and the drift velocity that describes the phase transport. And we actually do not need to check the phase velocities in previous models, since we can directly compute the drift velocity from the fluid motion. This is possible because the previous method uses an assumption that the phases are under a local equilibrium. In this case, drift velocities can be computed analytically, depending on the density and the acceleration of the fluids, as shown in the formulation on the bottom right corner. Then we only need to solve for the mixture velocity, just like in a single-phase fluid solver, where there is only one velocity field to be solved. This makes the method both efficient and compatible with any single-phase approach. For example, we can use IISPH or DFSPH or other methods. However, this is not suitable for non-equilibrium cases, where the phases are not under a local equilibrium. Then, the inertial effects of the phases, if we use the previous methods, largely eliminated. This generates less visual detail or even incorrect results. Let's watch a comparison between our method and the previous one. In this case, a uniform mixture of the two phases is released into a tank. The two phases immediately separate from each other. But in the previous method, the two faces only separate locally and form clumps. By using our method, the two faces become separate layers smoothly. To solve this problem, we propose a dynamic mixture model. The new solution focuses on keeping the inertial effects of the component faces. Therefore, we track the phase velocities explicitly. We can compute the mixture velocity and drift velocities on the fly using the definition. This brings us a totally different scheme of updating the velocities of the fluid. But note that we need to enforce the incompressibility of the mixture rather than of each phase. Therefore, we compute the pressure to enforce the divergence-free condition of the mixture velocity and apply this pressure to the component phases. This is the workflow of our method. We use WC-SPH since it's simple and effective. Incompressible solver like RL-SPH can also be easily applied as well. We highlight the multiphase part and show the difference between our method and the old one. We first sort the particles, compute density and pressure with the equation of state. Then we update the phase velocities. I'll show the formulation later. Then we apply drag force, since there is friction between the phases. After that, we update the mixture velocity, the position of the particles, then we compute drift velocities and the phase transport. In the old method, we first update the mixture velocity and the position, then we compute drift velocities analytically. The phase velocities are not tracked, and the inertial effects are lost. Now we briefly look at the formulations. The mixture velocity is defined as the average of the phase velocities weighted by the volume fraction. This definition satisfies divergence-free condition if all the phases are incompressible. The momentum equation of phase K is shown here. As we can see, P is the fluid pressure, τ is the viscous tensor, G is the gravity, and Mk is the drag force. For simplicity, we assume the phases are under the same pressure and viscous stress, where the pressure is computed from the fluid density. The viscosity is less important here, and we use the artificial viscosity as in the original WC-SPH method. The drag force has a linear form proportional to the relative velocity. To apply the drag force, we predict phase velocity without the drag force to get a predicted mixture velocity. Then we apply the drag force in a backward Euler fashion. After the velocity update, we only need to compute the phase transport. This part is relatively easy, as we can compute the drift velocities by its definition. That is, the phase velocity minus the mixture velocity. Then the transport is given by this divergence formulation. Note that this divergence only captures the relative motion of the phases. We need to add diffusion process manually and get this last formulation. The first term is motion induced, while the second term describes heat diffusion or turbulent diffusion. Still, we need to prevent negative volume fractions due to numerical error and the discretization. An iterative correction is applied to prevent negative values during phase transport. Please refer to the paper for more detail. Here we show the phase transport with and without the correction. With our iterative correction, we control the error to around 0.01%. In previous methods, a simpler correction manages to control the error around 1%. The improved accuracy may be less obvious in visual effects, but can be helpful in cases where the mass conservation is highly important. In this case, we show that our method also captures the fast mixing of the phases when driven by a moving boundary. Here we show the particle view of the bubbly wine. As we can see, the two phases separated rapidly. In this case, we use phase velocities that add up to zero mixture velocity to simulate phase transport in a static geometry object. Since we track the phase velocities, we can add force to individual phases to control multiphase flows. Control forces are added right before updating the phase velocities. Here we use a combination of force fields and control particles to modify the shape of the pink phase. We can also apply a spatial force field generated from an image. This makes it possible to control the color of the mixture. Finally, we show that by adding attraction forces and drag forces, we can simulate this filtration scenario. As a conclusion, this work has three main contributions. First and foremost, we present a dynamic non-equilibrium mixture model for a much wider range of multiphase visual effects. Secondly, we propose a robust phase transport regime to ensure mass conservation to a much higher precision. And last, we show a simple and flexible way to edit multiphase flows with control particles and force fields. Still, our method has several limitations. We find that with a fixed resolution, the phases cannot perfectly separate from each other. For example, an isolated particle is not able to separate into two smaller parts. These subparticle scale effects are not captured. In this work, we only consider Fourier diffusion, while non-Fourier diffusion may suit non-equilibrium cases better. We would like to further investigate variable viscosity and non-Newtonian phenomena in the future. Thank you for watching this presentation. I'm happy to answer questions if there is any. Please contact me with this email, and have a nice day.